Okay, in this example, this is a tension problem. And it's a mathematical tension problem where we're going to actually do a quantitative calculations, okay? So the only formula we have for tension is equal to delta P times R, okay? Let's read the question. An artery increases in cross-sectional area as it approaches the heart. Oh, weird. Okay, so that's weird. The arrow is pointing that way, but the heart is over here, and we see that the area is larger. Okay. Given that the flow speed and tension of the narrower part of the arteries are okay, so they gave us the flow speed, the tension, and the radius. Find the tension in the wider part of the artery where the area has doubled. So, tension seems to be in newtons per meter. It seems to be acting like it's almost a pressure, but it's not. We look at this formula or this picture, and it seems to be a Bernoulli equation problem. Okay, I'll tell you, it is. Okay, it's a Bernoulli equation problem. It's also a tension problem, and it's also a continuity equation problem. So I'm going to write down here before we go forward. Now we're going to write down all of the equations. Ready? So we're going to write down, first of all, we're going to be using tension is equal to delta P times R. And we can say tension wide, delta P wide, radius wide. And over here, we're going to write down tension narrow is equal to difference in pressure narrow, radius narrow. Next, we're going to write down that flow is equal to area wide times what? Velocity wide. Flow is equal to the same thing. Area narrow, velocity narrow. They're equal. Let me see. The Bernoulli equation says that pressure wide plus rho g h wide plus 1/2 rho v wide squared is going to be equal to pressure narrow plus rho g height narrow plus 1/2 rho velocity narrow squared. Okay, there are a lot of variables here, and what was given was the velocity narrow was equal to 1.5 meters per second. They told us the tension narrow was equal to, what was it? Was it 100? 100 newtons per meter. And they gave us one more value. The radius narrow was 2 millimeters. Radius narrow was equal to 0.002. They didn't give me diameter, they gave me radius, they gave it in millimeters, I'll put it in meters. So if we look at these, we've got 1, 2, 3, 4, 5 equations, okay? And actually these two are equal, okay? So it's, okay? So how many unknowns do we have? Or how many variables do we know? Okay, we've got the velocity on the narrow side. It's blood, right? So the density is 1050. What about the heights? Oh, you know what? The heights are the same. Okay, so because it's drawn horizontally, right? So we're going to cancel these two. Yeah, that drops. Makes it simple. Velocity on the wide side. Oh, we don't have that. We only have the narrow side. Okay, so this is question mark. Wait, pressure on the narrow side. Do we have the pressure on the narrow side? No, we don't have that. We have the tension. It's not the same. We have the pressure on the wide side? No, we don't. Okay, so we basically have 3 questions. And in Bernoulli's equation, right now, we only know the density and the velocity on the narrow side. We've got some figuring out to do. Okay, so how are we going to figure out what the pressure wide and pressure narrow are? Well, ready? Look at this. First of all, what we can do is we can say T wide is equal to delta P. What's delta P? Pressure wide minus pressure out. That's what delta P is. That's very important. Delta P in the tension equation is the difference between the pressure inside versus outside. And positive is when the pressure inside is larger, right? So it's going to be pressure, what we call pressure wide minus pressure out is delta P, and then RW. Well, I'll keep it as RW. And so then we want to solve for PW. So we're going to say PW is equal to tension wide over R wide plus P out. And I'm going to put a box on it because I like it. And then we can do exactly the same thing for this one. And I can just rewrite it. Tension narrow, using the same arguments. I don't have to go through the whole thing again. We can say this. Okay, so we can substitute those in, and now Bernoulli's equation doesn't have pressure W and pressure narrow. It has the tensions. Let's plug it in. It's going to get a little long, but it's worth it. Ready? TW over RW plus P out plus 1/2 rho VW squared is equal to tension on the narrow side over the radius on the narrow side plus P out, okay, plus 1/2 rho VN squared. You know what? I'm going to get rid of the parenthesis. There's no reason to put it there. And there. So is there anything else we can cancel here? Yes, there is. We can cancel these P outs. They're the same on both sides. And we wanted to figure out what the tension on the wide side was. So why don't we solve for it? So we're going to multiply everything by RW and throw everything to the right side. Ready? Tn Rn plus 1/2 rho Vn squared minus 1/2 rho velocity on the wide side squared. Okay. We have the tension normal, they gave it to us. I'm going to put a little check there. The radius normal, tension on the narrow side, they gave it to us. Radius on the narrow side, they gave it to us. The density, we know that. The velocity on the narrow side, they gave it to us. The density, they gave it to us. Hey, it's just the velocity on the wide side. How are we going to figure that one out? They told us that the area, okay, was 2A and A. Okay, so that's enough to be able to figure out the velocity. That's very important. We say that Q is equal to area wide, velocity wide, is equal to area narrow, velocity narrow, which is equal to 2A velocity W is equal to A velocity narrow. And finally we write, we can cancel the A's, and it just says that velocity on the wide side is equal to 1/2 the velocity on the narrow side. Oh, that's equal to 1.5 divided by 2, that's meters per second, is equal to 0.75 meters per second. Da, da, da. So now we even have the velocity. Radius on the wide side, do we know that one? Oh, brother, not yet. How are we going to figure out the radius on the wide side? I'm going to find a little nook to figure this out right here. I'm going to try to find it right here in this little space here. We're going to say that area on the wide side is equal to pi r wide squared. And the area of the narrow side is pi r narrow squared. And we know the ratio of the two is 2 to 1, right? We can say that area wide over area narrow is equal to rw squared over r narrow squared, I canceled the pi's, is equal to 2. That's what was given, because it's 2a over a. And so that means that rw is going to be equal to square root of 2. Oops, I'm going to get rid of the square. Times r narrow. Rw is equal to, r narrow was 2 millimeters, right? So what's square root of 2 times 2 millimeters? 2 square root times 0.0002 equals 0.0028. That's important. And so now we even have that one. So now we have everything. You plug it all in. And now that we've done all of that, I can show you another version where it's all typed out. If that helps, you can look at that one instead. And you get the velocity that we figured out, right? The velocity on the wide side was half of the velocity on the narrow side. Just because of the ratio of the areas, the radius on the wide side is 2.83 millimeters. The tension is this formula. That's very important. Very important to realize that delta P is not equal to narrow minus W. That'll be a quick mistake. This is everything as I said. You plug all the values in and you should get 144 newtons per meter. So tension on the narrow side was equal to 100 newtons per meter, okay? And on the other side, it's 144 newtons per meter. That's a monstrous problem, okay? The most important thing to learn from this is what? Well, this was the 3 equations, 3 unknown, right? It was the continuity equation, Bernoulli equation, and the tension equation. The other thing that's really important is to understand that in tension is the difference in pressure, just like with soap bubbles. It's the difference in the pressure inside minus outside, okay? And so you actually have to do that on the wide side of the artery and the narrow side of the artery. That is important, okay? So, yeah, in a way, I guess it's actually 5 equations. It's many equations, right? We also have to use the area of a circle. It's a lot of equations. That's the problem, okay?